Welcome to our presentation on chirality and optical isomerism. Chirality is a geometric property of molecules that are not superimposable on their mirror images. Just as your left hand cannot perfectly align with your right hand, chiral molecules exist in two mirror image forms called enantiomers. This concept is fundamental to stereochemistry and has profound implications in biology, medicine, and the pharmaceutical industry. In this presentation, we explore the definition of chirality, stereogenic centers, the R and S naming system, optical activity, racemic mixtures, meso compounds, and the importance of chirality in nature and drug design. We will work through 5 quiz questions and 5 detailed problem solutions to solidify your understanding of this essential topic. The word chirality comes from the Greek word chair, meaning hand. Your hands are the perfect analogy. They are mirror images of each other, but cannot be superimposed. In chemistry, a molecule is chiral if it cannot be superimposed on its mirror image by any combination of rotations, translations, and conformational changes. The most common cause of chirality in organic molecules is a carbon atom bonded to 4 different substituents. This is called a stereogenic center or stereocenter. A molecule with one stereocenter exists in 2 enantiomeric forms that are non-superimposable mirror images. These enantiomers have identical chemical and physical properties in achiral environments, but behave differently when interacting with other chiral substances, including the receptors in our bodies. The most common stereogenic center is a tetrahedral carbon atom with 4 distinct substituents. When all 4 groups attached to a carbon are different, swapping any 2 groups produces a stereoisomer. This carbon is labeled with an asterisk. The 2 possible arrangements around the stereocenter are called absolute configurations and are designated as R, from the Latin rectus meaning right, or S, from the Latin sinister meaning left. For a molecule with one stereocenter, there are exactly 2 to the power of 1 equals 2 stereoisomers, which are the enantiomers. For n stereocenters, the maximum number of stereoisomers is 2 to the power of n, though some combinations may yield identical meso compounds due to internal symmetry. Assigning R or S configuration requires ranking the 4 substituents by priority using the Cahn Ingold Prelog rules, also known as the CIP rules. Rule 1. Higher atomic number gives higher priority. If atoms are the same, move to the next atom along the chain. A double bond counts as if the atom is bonded twice. Rule 2. If the first atom is the same, compare the next atoms in each substituent until a difference is found. Rule 3. Multiple bonds are treated as equivalent to the same number of single bonds to the same atom type. Once priorities are assigned, orient the molecule so that the lowest priority group number 4 points away from you. Trace a path from 1 to 2 to 3. If the direction is clockwise, the configuration is R. If counterclockwise, it is S. One of the most distinctive properties of enantiomers is their interaction with plane polarized light. When plane polarized light passes through a solution of a chiral compound, the plane of polarization rotates. This phenomenon is called optical activity. One enantiomer rotates the plane clockwise, which is called dextrorotatory and designated with a plus sign. The other rotates it counterclockwise, which is called levorotatory and designated with a minus sign, by exactly the same amount. The rotation is measured using a polarimeter. The specific rotation is the observed rotation normalized for concentration and path length. The specific rotation equals the observed rotation divided by the path length in decimeters multiplied by the concentration in grams per milliliter. The D specifies the sodium D-line wavelength of 589 nanometers, and T is the temperature. Molecules with multiple stereocenters can form 2 types of stereoisomers, enantiomers and diastereomers. Enantiomers are non-superimposable mirror images. They have opposite configurations at every stereocenter. Enantiomers have identical physical properties in achiral environments and differ only in their optical rotation. Diastereomers are stereoisomers that are not mirror images. They have opposite configurations at some, but not all stereocenters. Diastereomers have different physical properties, different melting points, boiling points, solubilities, and spectroscopic characteristics. This difference in physical properties is key to separating stereoisomers. While enantiomers require chiral resolution techniques, diastereomers can often be separated by ordinary physical methods like crystallization or chromatography. A racemic mixture, or racemate, is a one-to-one mixture of two enantiomers. Because the equal and opposite optical rotations cancel, a racemic mixture shows no net optical activity. Racemic mixtures often have different physical properties from the pure enantiomers. For example, they may have different melting points and different solubilities. Chiral resolution is the process of separating a racemic mixture into its individual enantiomers. Methods include preferential crystallization for conglomerates, formation of diastereomeric salts with a chiral resolving agent, chiral chromatography using a chiral stationary phase, and kinetic resolution using enzymes. The enantiomeric excess measures the purity of an enantiomer. The enantiomeric excess equals the absolute difference between the percentages of R and S divided by their sum times 100%. Nature is fundamentally chiral. All naturally occurring amino acids except glycine are L amino acids which have the S configuration, and all natural sugars are D sugars. This homochirality is essential for life. Enzymes, which are themselves chiral, can distinguish between enantiomers of a substrate. In pharmacology, chirality is critical because drug enantiomers can have dramatically different biological activities. The most famous example is thalidomide. One enantiomer was effective as a sedative, while the other caused severe birth defects. Today, many drugs are sold as single enantiomers rather than racemic mixtures. Examples include escitalopram for depression, naproxen for inflammation, and ibuprofen. The food industry also cares about chirality. L-aspartame tastes sweet, while D-aspartame is tasteless. A meso compound is a molecule with multiple stereocenters that is achiral due to an internal plane of symmetry. Despite having stereocenters, the molecule as a whole is superimposable on its mirror image. The classic example is meso-tartaric acid. It has two stereocenters, but possesses a plane of symmetry between them. Meso compounds have the RS configuration when the stereocenters have opposite configurations. A molecule with two stereocenters can have 4 stereoisomers maximum. But in the case of tartaric acid, the two enantiomers are R, and S, and the meso compound R, S equals S, R due to symmetry, so the total is 3, not 4. Meso compounds are optically inactive despite containing stereocenters. The presence of a plane of symmetry makes the molecule achiral. While tetrahedral stereocenters are most common, chirality can arise from other structural elements. Axial chirality occurs when substituents are arranged around an axis rather than a point. Examples include allenes with different substituents at each end, biphenyl compounds with restricted rotation called atropisomers, and substituted spiro compounds. Planar chirality arises in molecules where a plane replaces the point as the chiral element. This is seen in substituted cyclophanes, trans-cycloactene, and certain ferrocene derivatives. Helical chirality occurs in molecules that adopt a helical shape, such as helicenes, which are polycyclic aromatic hydrocarbons that form a spiral. The handedness of helices is described as M for minus or left-handed, or P for plus or right-handed. In each case, the molecule lacks a plane of symmetry and exists as two non-superimposable mirror images. Quiz question 1. Which of the following is the defining characteristic of a chiral molecule? Option A. It contains a double bond. Option B. It is not superimposable on its mirror image. Option C. It contains at least one oxygen atom. Option D. It rotates plane polarized light to the right. Take a moment to think about your answer. Quiz question 2. How many stereoisomers are possible for a molecule with 3 stereogenic carbon atoms? Option A, 3. Option B, 6. Option C, 8. Option D, 9. Think carefully about the maximum number of stereoisomers formula. Quiz question 3. A solution of a chiral compound has an observed rotation of plus 15.2 degrees. The path length is 1.0 decimeter and concentration is 0.050 grams per milliliter. What is the specific rotation? Option A, plus 76 degrees. Option B, plus 152 degrees. Option C, plus 304 degrees. Option D, plus 760 degrees. Quiz question 4. Which of the following statements about diastereomers is true? Option A. They are mirror images of each other. Option B. They have identical physical properties. Option C. They have the same configuration at every stereocenter. Option D. They have different physical properties. Quiz question 5. What is the enantiomeric excess of a mixture containing 75% R enantiomer and 25% S enantiomer? Option A, 25%. Option B, 50%. Option C, 75%. Option D, 100%. Problem 1. Assign R or S configuration. Part A. A carbon with priorities 1 equals bromine, 2 equals chlorine, 3 equals fluorine, 4 equals hydrogen. The path from 1 to 2 to 3 is clockwise when priority 4 points away from the viewer. Since clockwise gives R configuration, the answer is R. Part B, a carbon with priorities 1 equals OH, 2 equals CH2, CH3, 3 equals CH3, 4 equals H. The path from 1 to 2 to 3 is counterclockwise when H is pointing away. Counterclockwise gives S configuration. The specific rotation formula allows us to calculate this precisely. Problem 2. Specific rotation calculation. A 0.250 gram sample of a chiral compound is dissolved in 10.0 milliliters of ethanol and placed in a 2.00 decimeter polarimeter tube. The observed rotation at 25 degrees Celsius using the sodium D line is plus 4.82 degrees. First, calculate the concentration. 0.250 grams divided by 10.0 milliliters equals 0.0250 grams per milliliter. The specific rotation equals the observed rotation divided by path length times concentration, which is plus 4.82 divided by 2.00 times 0.0250, giving plus 96.4 degrees. Specific rotation is an intrinsic property and does not change with concentration. For a sample with 75% enantiomeric excess, the observed rotation would be plus 3.62 degrees. Problem 3. Stereoisomer count with meso compound. 2. 3. Dibromobutane has 2 stereogenic carbons. The 4 possible combinations are R, 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 S, S, R, and S, S. The RR and S forms are a pair of enantiomers, mirror images with opposite configurations at both centers. However, the R, S, and SR forms are actually the same molecule because there is an internal plane of symmetry between the two stereocenters. This is the meso compound. So instead of 4 stereoisomers, we only have 3. The R enantiomer, the S enantiomer, and the meso compound. This is a classic example of how internal symmetry reduces the number of stereoisomers. Problem 4. Optical activity of a mixture. The pure R enantiomer of a compound has a specific rotation of plus 120 degrees. A mixture of R and S enantiomers has an observed rotation of plus 0.36 degrees in a 1.0 decimeter tube at a concentration of 0.010 grams per milliliter. The specific rotation of the mixture is plus 0.36 divided by 1.0 times 0.010, which equals 36 degrees. The enantiomeric excess equals specific rotation of the mixture divided by the specific rotation of the pure enantiomer, which is 36 divided by 120, or 30%. This means the mixture is 65% R and 35% S. Problem 5. Racemic resolution by diastereomeric salts. A racemic carboxylic acid, a mixture of R and S enantiomers, must be resolved. It is treated with a chiral base, Sb, which is 100% enantiomerically pure. Two salts form, Ra combined with Sb and Sa combined with Sb. Are these salts enantiomers or diastereomers? They are diastereomers because both salts contain the S configuration at B, so they are not mirror images. Since diastereomers have different physical properties, they will have different solubilities. One salt will crystallize preferentially. After separation, pure Ra is recovered by adding a strong acid like hydrochloric acid to reprotonate the carboxylic acid. The chiral base can be recovered and reused. Let us consolidate everything we have